Hi class, this last section of Chapter 6 talks about telescopes and the different light that they can see and how you can make different telescopes see different types of light throughout the electromagnetic spectrum, and also how we can make telescopes work together to kind of simulate a much larger telescope. So we don't just want to look at visible light coming from an object. We want to look at all the different forms of electromagnetic radiation. So radio waves are kind of like what you get from your satellite. If you have a satellite dish on your house, that's a telescope. That's something that's receiving and focusing light from some object, and that happens to be a satellite out in space. So this dish is really like a mirror that reflects radio waves, or maybe microwaves, longer wavelength light, into a receiver here, and that gets turned into an electrical signal and fed into your house, basically into your television ultimately. And so radio waves are detected with dishes that look like mirrors, but they're not shiny because they don't reflect visible light very well, but they do reflect radio waves very, very well. So here's a big radio wave telescope in Arecibo, and it's built into a valley, and it can't move. It's just sort of sitting there. And so you think, well, what kind of use is that? Well, they can point it a little bit by moving this detector around. So this is the radio waves come down and they bounce off and they go into this detector. They can move this around a little bit to kind of give it a little bit of directionality, but really this mainly just sees straight up. And so they have to wait for an object to they have to wait for the Earth to rotate for whatever object that they're looking for to be in the field of view. So it's not, it's very large, so it's got a very good angular resolution, but it's not as useful because they can't really steer it very well. But it's been around for a long time, and it's still in use, but there are other telescopes now, dishes that they've created that aren't quite as big all by themselves, but altogether they make a much larger telescope through the process of interferometry that we'll talk about later. So this is the radio wave telescope. That's a giant mirror. It doesn't look shiny, but it is shiny to radio waves, and it shines the light back up into this detector. Infrared light and ultraviolet is stuff that a kind of a normal telescope can see, can reflect. You use mirrors very similar to what you use in a visible light telescope. The problem, as we've talked about before, is that with infrared light and ultraviolet light, those particular forms of electromagnetic radiation don't penetrate very well down to the surface, and so they have to be higher up in the sky. And so this is the Sophia telescope that's flown on a 747, and the airplane just flies really high in really smooth air, and they look at things through the telescope. They have computers in there and everything. The whole airplane is an observatory. And then this is the Spitzer spacecraft, or telescope out in space, and it also looks at infrared and ultraviolet, and it looks at a lot of different things. And there's actually a nice website they have. You should look up these telescopes, Google these telescopes, and find their main webpage. There's a lot of useful information, a lot of neat tools that you can read about. They have a lot of activities for younger kids to kind of help them understand what's going on, what these telescopes are seeing. There's some really neat websites. We'll look at the Spitzer website in a second. X-ray telescopes are also put out in space because X-rays don't reach the ground at all. And they're actually much harder to collect. X-rays being much higher energy, they're very hard to focus and to actually capture. And so the design of an X-ray telescope is very different from the design of a visible light or radio wave telescope. This is the Chandra X-ray Observatory. This is out in space as well, and there's a good website for that too. So the mirrors that you see in an X-ray telescope don't look at all like the mirrors you see on a visible light telescope. If you had a mirror, if we go back for a second, if you had a mirror like this, just a dish-like thing, whether it's a glass mirror for a visible light telescope or this mirror that we see here for the radio waves, if X-rays came down and hit it, they wouldn't bounce off and go to a focus point. They would basically just pass right through. So what you need to do is you need to construct the mirror so that the X-rays barely hit the mirror. They come in and they kind of hit the mirror in a very glancing angle. They just skim the surface. And in doing that, they don't necessarily penetrate through it and get absorbed by it or anything. They just kind of skim off of it. And if you do that a couple times, you can gradually change the direction, the trajectory of those X-rays, and eventually bring them to a focus to form an image. So these are mirrors. These are X-ray. This is an X-ray telescope mirror. It's very weird. It's all these concentric cylinders that gradually focus the X-rays down to a point on some device that can capture them and measure their wavelength, and thereby measuring their energy. So it's not an easy thing to do. Gamma ray telescopes also exist, and they're even harder to collect. This doesn't look like a telescope, but it is. It's got an opening where it points toward objects and just collects gamma rays coming from the objects. This is the Fermi Gamma Ray Observatory, and it of course also has a website. It's a good one to look at too. So these are very hard to collect, but in a similar way, you try to let the gamma rays go in and barely interact with things to just kind of gradually change their trajectory, or somehow absorb them in some way where you can measure their wavelength, measure their energy. It's not an easy thing to do. And then other things we can observe are, besides light waves, and this has been fairly recent, is gravity waves. So Einstein's theory of relativity predicted the existence of gravity waves, and what they are like oscillations in the fabric of space and time itself. And this is an observatory. This is the LIGO Observatory. There's 2 of them in the United States. It's two really long tubes that they send a laser down. There's a mirror at the end. One laser beam goes this way and bounces off the mirror and comes back. The other laser beam goes this way, bounces off a mirror and comes back. When those 2 laser beams combine, they form a particular pattern, some kind of what they call an interference pattern. And if a gravity wave comes along, it gradually, very gradually, can change the length of one tube compared to the other. Very, very small changes. But that makes very small changes in these very long tubes makes a fairly big change in that pattern that you see when the 2 laser beams intersect. And so by looking for changes in the pattern that you see, you can detect these gravity waves that are very, very weak. And they have detected gravity waves now. It has been confirmed that they do exist, and they detected what they believe to be gravity waves coming from the merger of 2 black holes, or possibly even 2 neutron stars. And when they merge, they sort of send the shock wave of like gravity ripples through space and time. That's all been predicted by Einstein's theory of general relativity, and it's been verified by the observation of these gravity waves, I believe, in October of 2015 or so, if I'm remembering right, somewhere a few years back. But they've detected more gravity waves since then, so they're pretty confident that what they are detecting are in fact these gravity waves, and it is a confirmation of Einstein's theory of general relativity. And there's also observatories that detect neutrinos. Those are observatories that are deep underground, and we'll talk more about those later on when we talk about the sun. The sun is a source of neutrinos. Neutrinos are fundamental tiny particles, kind of like electrons, sort of. And there's also cosmic rays. Cosmic rays are just really high energy things coming from space, mainly protons that come from some extreme event. It could be explosions of stars, white dwarfs, or not white dwarfs, supernova that explode, stars that explode. So we'll talk about those explosions eventually. But these are very energetic things that come, and they often hit our atmosphere and create other particles that then rain down upon us. But luckily our atmosphere protects us from these cosmic rays. So there are observatories also that detect these other things that are not electromagnetic radiation. So we can also take telescopes and make them work together. So this is the Very Large Array. This is down in New Mexico. There's a bunch of these big dishes. Each individual dish is nowhere near the size of the Arecibo radio telescope, but all these dishes can combine together to kind of have the effect of a very large telescope. And if you look at the Very Large Array, it's like a Y-shaped arrangement of telescopes, and they can move around on basically railroad tracks. And they can literally, when you combine the images of all these telescopes, the effect, the angular resolution you get is the same as if you had a telescope that was a couple miles in diameter roughly. So it has the effect of giving you the angular resolution of a very, very large telescope. But again, this is observing in radio waves, not visible light. So this is kind of the idea, is that you get light collected by this telescope and light collected by this telescope. They're a certain distance away. Well, that's the same as if this light coming into this telescope hit this part of this huge telescope, and this light coming along, if it hit that telescope, or whatever light hit that telescope would have hit this part of this big telescope. And yeah, maybe we're ignoring the light that would have hit in here, so we don't have as bright of an image, but we still have the effect of having a very large size. We can effectively get light that would have hit here and would have hit here, but it's hitting these smaller telescopes instead. So adding these smaller telescopes together gives you certainly a little bit brighter image than one telescope alone. It doesn't give you as bright of an image as the big, large telescope would, but it does give you an equivalent angular resolution that the large telescope would give you. And that's really the most important thing, is getting really good angular resolution to really pinpoint the position of different objects in the sky. So that's called interferometry. So here again is the very large array. It doesn't really show you the picture here, but if you look that up, if you Google that, you could find an image of the very large array from the air, and you could see the pattern of telescopes and how they're spread out. So this basically was about looking at different forms of light and how we can collect them with all these different types of telescopes. So let's just go to the web page for the Spitzer telescope. So if you just Google Spitzer, you'll find the website is spitzer.caltech.edu. And this is the main homepage. And there's all kinds of neat stuff here. You can read about the actual mission. You can see it's been 5,148 days since it was launched. This is how far it is from Earth right now. And you can read more about the mission. If you go to images, you can see all kinds of different images, both photographs and artwork that people have submitted. You can go to Explore the Mission, or you can go to Explore or the Mission. So if you click on Mission, it gives you different things. So down here, it shows you the science behind the various missions. The telescope looks at stars. It looks at planet-forming disks. So it looks at really young stars and to see if there are planets forming around them. Planet-forming regions are very bright in the infrared, so this is a useful telescope for studying how planets are formed. Exoplanets, to look at planets around other stars. The infrared telescope is also very useful for that. And then looking at galaxies and other objects in the universe, everything gives off infrared light. And so, looking at all these different things in all these different wavelengths of light gives you a more complete picture of what's going on out in space. So this is there's all kinds of information here. Go to Explore here. There's things for kids. There's screensavers. You can download a screensaver. You can get posters of images and things. You can get models of the telescope or look at models of it. There's all kinds of educational resources here, different experiments that you can read about and sort of kind of do small versions of in your classroom if you're a teacher. So there's all kinds of fun things. Virtual telescopes. These are all neat things to look at. So I highly recommend that you play around with these websites for these big telescopes out in space: the Spitzer telescope, the Fermi Gamma Ray telescope, the Chandra telescope, the Hubble Space Telescope. Yeah, there's all kinds of interesting information out there. So that wraps up Chapter 6. And a lot of these ideas we're going to be coming back to when we start looking at galaxies. We'll start studying stars and galaxies and how they are created, how they kind of live their lives, evolve, and so on, and ultimately how they die, how stars die. It's pretty interesting. So we'll be getting into the lives of stars coming up soon.